But before we get to the brake horsepower, I want to look at the suction lift one more time and a piece of that suction lift. What we call net positive suction head, NPSH. So we have a water surface, a pump above that water surface, a suction pipe down into that water surface. The bit of information we need to know about how this pump can lift that water is we need to know the net positive suction head of that pump. How much suction can it pull? How much can it suck? And so every pump has a characteristic that will delineate this amount of lift capability. And it's called NPSH, or net positive suction head. Now the NPSH is not just made up of elevation, it's also made up of friction loss, velocity head, and the pump's ability to create a suction. And also the temperature of the water. The vapor pressure will have an effect on this. The greater the temperature of the water, the less suction capability a pump has. Also, the greater the altitude you are above sea level, the less suction capability a pump has. Because we get higher in altitude, the air gets thinner, the basic atmospheric pressure drops, and therefore we have less lift capability. When water gets warmer, it expands because it's banging against each other. The molecules are spreading out a little bit and becomes less dense, therefore you have less suction capability. So that's kind of the little twist behind net positive suction head. A pump that may work just fine in Seattle may not be able to lift water in Denver. You got a mile's difference in altitude. A pump that might work just fine with 50-degree water might not work at all with 120-degree water because of the change in the temperature of the liquid. It just won't be able to lift it that high. It reduces the lift capability.
What does heat do to the suction again?
The question is, what does heat do to the water so that it won't be able to lift? It expands the water. So you have less density. So it makes it more difficult for it to be sucked up. The water density is reduced, which reduces the suction capability of the liquid.
So what would be the main differences between a pump used in Seattle and one used in Denver?
The main difference between a pump used in Seattle and Denver is that you just have to be real careful that you don't abuse the suction lift capability of that site. You have to know what the pump's capability is, and it's something that can be numerically calculated. Okay. And every pump set that you have, you must do an evaluation of its net positive suction head.
Okay, so what things can you change internally in the pump that will make it?
What can you change in the pump? Absolutely nothing. A pump has a given net positive suction head available, or actually in this case required. The pump requires so much net positive suction head, and it's just the way it is. So if that pump, it may not work in Denver, you have to choose a different pump because it just flat won't work there. Now what you could do is move it closer to the water surface. That'd be a way to help yourself. Or reduce the friction loss coming up the tube by making a bigger suction pipe. That could be a way. But the pump itself is not, you can't do anything to the pump itself. It has a given characteristic and it's not going to change. And it's called the net positive suction head required for each individual pump. Every pump has a required amount.
You said you could improve it if you lowered it, but wouldn't you still have to have the pushing capability? Wouldn't that affect, wouldn't the temperature of the water or the atmospheric pressure have the same effect as far as creating the surge as the actual lift?
Well, the question is lift versus the discharge head. Is there, by reducing the discharge head, by coming closer to the surface of the water, then it'll have to do more work on the other end. So it's going to have to do more, it'll have less suction head because you've moved it closer to the water surface. It's going to require more discharge head to still get it to the same elevation you were after. Because remember, the elevation we're working from is water surface to discharge point out there, wherever that discharge point is. So the water surface is the key. We don't care where the pump sits as far as the dynamic package is concerned. The only problem with the pump, if it gets too far above the water, it just won't be able to draw water. But it still has the same total head that it has to overcome, because it's just a linear measurement in the vertical distance that it has to overcome. We're dealing with a verticality of this system. Now, as far as length is concerned, the horizontal, that has to do with friction loss. It doesn't take more energy for the pump necessarily to move at 100 feet versus 1,000 feet, except for the difference in the friction loss if it's flat. There'll be more friction loss, obviously 10 times more friction loss in a 10 times longer pipe.
So once you get it up there, then it's the same?
Yeah.
So when you're going to put a pump in a new field that doesn't have one or anything, and you're going to have to measure or take the temperature of the water, and how are you supposed to know the elevation of sea level and all the atmosphere?
Okay, so
everything